Let us begin. Dames en heren, ladies and gentlemen, geachte collega's, dear colleagues, I hereby formally open this session and welcome you to the public defense of Olivier Verhamme. Let me first present the jury members and the supervisor of Olivier. I will start with supervisor. We have here John Sundqvist and Hugh Sana from KU Leuven, and Alex de Cotter from University of Amsterdam, the Netherlands. We also have the Paul Krauter as a jury member from University of Sheffield, and Enrico Carlton from KU Leuven. Jury members Leen de Sien from KU Leuven and Julia Botsteiner from University of Amsterdam, the Netherlands, were excused because they were not able to participate today, but they asked all their questions during the preliminary defense. And my name is Jasmina Magdalenic. I'm also the KU Leuven professor. Please sit. Olivier Verhamme has presented to the faculty the PhD thesis on the topic spectroscopy of massive stars as low metallicity, studying the atmospheres and outflows of B stars, in partial fulfillment of the requirements for obtaining the degree of PhD in science, astronomy, and astrophysics. Olivier Verhamme shall now publicly defend the PhD thesis. Olivier Verhamme, you are invited to give a presentation of about 45 minutes about your work. Afterwards, the examination committee will ask questions and discuss your work with you. Please.
Thank you. Put it back. Turn it off first. Whatever. Okay, thank you. So my colleagues at this month have been gone through this 5 times. This is the 6th time for them, but that have me the opportunity to kind of gather a lot of inspiration on how to do these things. So for all my colleagues from the astronomy department, here goes number 6, and almost the last one of the month. So my subject, spectroscopy of massive stars at low metallicity, studying the atmosphere and outflows of B stars. I've worked on this for 4 years. My goal is here to kind of give you an overview that hopefully most, if not all of you, can follow along quite well. So let's start with getting on the same ground floor. What do we mean when we say star? What is an actual star? Well, a star is a ball of gas, of plasma, that is self-balancing. You have gravity on the one hand, because it consists of mass, and mass tends to attract each other. It just wants to contract, like a little ball wanting to constantly squeeze itself closer and closer together because there's a mass pulling it all together. But there is mechanisms that push it back. One of these mechanisms is gas pressure, just the same way as in a pressurized canister. The molecules are pushing against the edge of the canister. Here it is pushing against the material, pushing it back, giving it some force to work against. The second thing that's pushing it back is radiation pressure. Radiation pressure is not something you usually see in daily life, but it is the effect where if you have a lot of light, a lot of photons, a lot of light, a lot of radiation, it is able to push against the material and push it back outwards, keeping it in a balanced way all the time. Now, where does this energy come from? Because yes, I can say like, oh, there's this radiation and gas pressure, but it needs some sort of source. It needs an engine. And the engine of this happens in the core of the star. In the core of the star, hydrogen gets fused into helium, therefore producing some energy, and that energy gets converted into heat and radiation, heat and light, and that is what pushes against it in the end, because this heat gets converted into gas pressure as well. So once you have hydrogen in the core burning along, at some point you'll run out of hydrogen. You have a finite amount of hydrogen in the core. At some point it will be gone, and all you're left with is helium. At that point, the core will contract a little bit more, get a little bit hotter, and if there is enough material above it, if there's enough squeezing happening, so to say, the helium can be converted into heavier and heavier elements. But for that, you need enough mass from the outside to push it in. So the heavier the star, the heavier of the elements they can form. The end point is always iron. Once you have fused into iron, there's no more way to go, because fusing iron doesn't give you energy, it costs energy. So that's not a way to keep the star stable at all. At that point, the star will go, and you get a supernova, you get a black hole, or a neutron star. Now, stars are interesting in a lot of ways, but one of the things that not everybody always thinks about when they think about stars is they are the producers of pretty much all the elements you find on Earth. Because in the core they fuse all these elements, but also the heavier elements beyond iron are also created in some astrophysical processes. Some of them, when the boom happens, there's a lot of excess energy, and that can be converted into new elements, but also lower mass stars can have this same process in which it captures some extra neutrons, some extra protons, creating heavier and heavier elements. A side note here to make real quick is that astronomers tend to really shortcut this entire thing. We talk about 3 elements pretty much, that is hydrogen, helium, and all the other things are metals. We don't really care about what exactly are these other things entirely. There are some individual elements which you sometimes care about, but when you hear me say the word metals, don't think of iron, don't think of nickel, all these things. Think of everything that is not hydrogen and helium. It's just baseline. Okay, so that is the basics of stars. Let's now talk about massive stars in particular. Massive stars are those stars defined as 8 times more heavy than the sun. On this plot here, I'm showing you the luminosity compared to the sun of a star and the effective temperature. Effective temperature you can think of as surface temperature. So that's just how hot is the surface of the star. The effective temperature here is in the scale going down. So here are the hot ones, here are the cool ones. This is going to come up a lot. A lot of plots I'm going to show you are going to have the hot ones here, the cool ones here. And luminosity here is not in a linear scale, but in a log scale. That is also going to come up a lot. Log scale just means that you go from 1 to 10 to 100 to 1,000 in equally spaced steps instead of 1 and 2 being equally spaced steps. That means that the star over here doesn't have a luminosity that is 6 times larger than the sun, but it's 1,000,000 times larger than the sun. The stars I care about are located here in this diagram, which we call the HRD, or the Hertzsprung-Russell diagram. They're located over here. They are the hot, very, very luminous ones. Hot, I mean 10,000 Kelvin and above. Up to 30,000 Kelvin is the official B star regime, or what we usually refer to as the B star regime. I also looked at some even hotter stars, which you call the O stars. Because they're so luminous, there's a very large contribution of radiation pressure to keeping these stars stable. And as I will get into later, because there's so much extra luminosity, extra light, it can actually push out a lot of material that way as well. And that's what we call outflows or winds. They aren't horizontal winds like we have on Earth. They flow away from the star. So they get material into space, essentially. So why do we care about these massive stars? Well, massive stars are not the most common star you find around. Actually, they're way less common than lower mass counterparts, but they are still interesting for a couple of reasons. One, well, they have a lot of influence on the region they're around. If you look at galaxy evolution, so how stars form and die and how gas spreads, massive stars have a huge influence here because they have this large amount of radiation, they have these very strong outflows, they kind of govern the region they're a part of, and because they have these strong outflows, they also get these elements that they create in their core and kind of spew them back into the region around them, both during their life and when they go boom at the end. If you're interested in very fundamental physics, like how does gravity work in its most extreme forms, you're also likely somewhat interested in massive stars at least, because the black holes you can use to study gravity are the end products of these massive stars. We call the massive stars the progenitors of these black holes. So if you want to study black holes, you need to be somewhat aware of how massive stars work and need to understand how they live their life to get you to your endpoint where you actually want to look at. As I said before, they also produce a lot of heavy elements, so if you're interested in nucleosynthesis, where elements come from, they're also quite useful. Okay, so I've talked a lot about these massive stars now and their winds, but I haven't really explained how they actually launch these winds. To launch these winds, they need some sort of interaction between light and material. And to understand that, there are 2 basic concepts about the material and the radiation and the light you need to understand. First off, an atom like this, here I made a hydrogen atom with 1 proton in the middle and an electron at a specific energy band. This electron cannot be wherever. It is actually very limited to the energy levels it can be at. It has what we call discrete levels or quantized energy levels. So it can jump from this energy to this energy level and from this energy level to this energy level, but it cannot be somewhere in between. So it needs a very exact amount of energy to jump from one level to the next. It cannot just do willy-nilly whatever it wants. Another thing to understand is that light, as a concept, consists of photons, and these photons can have a lot of different energies. These different energies range from radio waves, in which they have very long wavelengths, very low energies, things you've used daily, probably radio waves, or they can get very energetic and they become X-rays and gamma rays, which you all also know. These are used for X-ray photographs, for instance, or UV light is the light that burns you if you don't put on sunscreen, but the actual light we look in, which is all the exact same thing, is only this little bit here that is from 400 to 700 nanometers. So all of these things, all of these processes, all of these things we usually talk about as very separate things are all just light. They're all just photons at different energy levels. But it means that, and stars actually produce light in this entire range, usually. So what can happen is a photon from the star travels, and it has the correct wavelength, the correct energy to interact with a specific material, and it excites the electron from its base level, in this case up to level 3. At this point, the photon gets destroyed because its energy has been converted from photon energy to an excited electron, but the momentum the photon had, because photons also have momentum, is converted into the actual atom itself. So the atom gains some velocity, gains some speed. If you do that over and over again, you can actually create some actual velocity fields. Now, later on, it can actually re-emit the same photon, or it could have gone through different stages where it emits 2 photons with lower energy by going to the second level and then the first level. But this photon is scattered in a random direction. Over many and many of these iterations, it will scatter. The momentum lost or gained from this is 0, because it's going to go in a random direction anyway. Now, what I talked about now, the example I gave was hydrogen. Hydrogen actually has a very limited amount of these transitions because it only has 1 electron. That electron can go from 1 to 3, like it's showed here in this diagram, which gives you the actual energy levels of the first and third level. It can go from 1 to 3, it can go from 1 to 2, and so on, and within this you can have some transitions. But this means that all the wavelengths it's actually sensitive to are just all the lines on this diagram. It's a very limited amount of wavelength that it can actually interact with. While other elements, such as iron, which have a lot more of these electrons, a lot more of these transitions, become this jumbled mess, meaning that they can have a lot of different wavelengths they can interact with. Each line here is a different wavelength that can be absorbed by iron, meaning that iron, even though it's way less common in a star, the most common thing in the universe by far is hydrogen, even though iron is so much less common, because it's so good at absorbing all this energy, it's actually the push that gives you the outflow. So to put this all together, you have your star. In a massive star, there's a lot of radiation coming from it, and your electron scattering, your electron transitions act as a sort of sail catching that light and pushing itself forward. So how do you determine, how can you think of this in a very direct way? There's 2 ways to increase the strength of your wind. You either need to produce more light, give it more energy to catch, or increase the size of the sails. And you can increase the size of the sails by making it more efficient to gather these electrons, adding more iron, for instance. You have more material that's really good at catching this wavelength, or getting your material in such a state, in such an energetic state, that it's very, very good at collecting all this light that's coming at it. This diagram is a little bit of an artist's impression of what a star actually looks like what the wind looks like around the star. So the star itself is, of course, in the middle, the blue dot, and everything around it, all the white stuff is its wind. The mass that it loses itself can be quite easily up to 1 solar mass, so 1 times the sun in 10,000 years. That sounds like a lot of time to lose 1 sun worth of mass, but these stars live a couple million years, so they can easily lose multiple solar masses quite directly. They're also really fast. If you look at what the velocity is, so how fast these outflows actually are at the very edge of let's say, this box, where there's no longer any interaction from gravity, there's no longer any interaction from the radiation field, they're very fast. They're thousands of kilometers a second. 2,000, 3,000 kilometers a second is quite normal to find these at. And that is very fast. 1,000 kilometers a second is extremely fast. So on top of that, you have these winds, but they're not homogeneous. They have these dense regions and low density regions. The low density regions we call the interclump region. This is the region that is sparse of material. There's not a lot there. We have a factor we use called FIC, or the interclump factor, to define how dense it is compared to average. And this is expected to be very low. It's the expectation before anything I did was about 1 to 10%. I'm going to come back to that clearly. The other regions, the dense regions, or the clumps, where the overdensities are, this is where the denser material lies. We also have a factor for that called FCL, or the clumping factor, which defines how much denser these overdensities are compared to average. So I've explained this entire theoretical setup of how we think these winds work, how they should behave, what we already know, what we don't know. And there's actually not a lot that I explained that we don't know. We seem to have a good theoretical picture of it. We seem to know a lot about the actual values of these things. So what is the problem? Why am I still here talking about these winds? Well, since the last 20 years, let's say, people have been able to take all these physics, put them into numerical models, and see what the actual mass loss rate is we predict for specific types of stars based on their mass, their luminosity, so how bright they are, and their temperature. And the first one of those that really got a lot of traction is the Vink prescription from 2001, and they showed this red one. Here on the x-axis, again, we have temperature going down to the right. Like I said, that's going to come up a lot. And on the y-axis here is mass loss rate, again in logarithmic scale, but here the minus stands in for it, which means that this star, this dot here, tells you that for a star with this specific temperature, it takes about 1 million years to lose 1 solar mass. That's a lot less than the number I was talking about before. It's about 100 times less than what I was saying before. And this first one looked good, and people were like, okay, that looks fine. There were some questions about this jump, but the main thing was like, okay, fine, whatever. And then in 2023 and 2024, people got these results out from Björklund and Kritichka, and they did not get these jumps. They did different assumptions. They, well, removed some of the assumptions, had some other assumptions, and they got very different behavior out. They do not have this bistability jump, as we call it, but they have this monotonic decrease. So the question now is, in this range where we see this large divergence, so not in the hot range, which we call the O-star regime, but in this still hot but cooler regime, which we call the B-star regime, we have this very big discrepancy between the different models. Here, at least, even though they're still spread out by quite a bit, at least they all seem to agree temperature go down, mass loss rate go down. But here, everything goes buck wild. Some go monotonically decrease, some have a jump, some have this bump thingy going on. So the question is, what is real? What is here, what is not here? The bistability jump itself, when it first came out, was actually thought of as a logical step, because at this temperature, iron 4, which means that it's triply ionized iron, so iron that has lost 3 electrons, recombines, regains an electron, and becomes iron 3. And that makes the sail bigger, meaning that mass loss rate must go up. And because this is quite a short temperature range, the fact that this was a discontinuity actually made sense. Now, we don't see this in these new models, even though they also have this recombination. So there's something going on we don't understand fully. Now, does this matter? We see this discrepancy in these mass loss rate regimes, sure, but is that all? Is the only thing you really care about the fact that there's different physics going on that they don't fully understand? Well, that enough is reason enough to be interested in it, in my opinion. But if you're not, it's also important if you're interested in how a star evolves, which is important for if you care about black holes, which is important if you care about the galaxy evolution, which is important if you care about these elements that get created. Because if you use the Vink prescription, which was the red one, and take a 60 solar mass star, run it through a whole bunch of time, model it in an evolutionary code, meaning that you in a computer tell it to now become much older, you'll end up with a 23 solar mass star that looks very hot, very small, very dense. This is what, well, very small. This is what we call a Wolf-Rayet star. It is very, very hot because it has such a high mass loss rate over its lifetime that it was able to shed the outer layers of the star. And therefore, it's revealing the hotter inside. If you instead use the Björklund rate, which was the white one, monotonically decreasing, we end up with a 47 solar mass giant, red supergiant. And this is very different because it was not able to expel its envelope, expel the outer layers of its star. It's looking a lot cooler. It has a lot more mass. If this eventually turns into a black hole, the black hole mass will be different as well. So it not only influences what we expect these black hole masses and stuff to be at, but also the type of stars we expect to find in the universe. So that was the goal, or that is the goal of my thesis. I want to improve our understanding of massive stars, of massive star winds. I want to know how much mass is lost, and if we're going anyway, might as well look at what the structure of these stars or these winds is exactly. So how do we study stars? That is the main thing we now need to figure out. Stars are these annoying objects that are never close to you, always very far away, and the only thing you get from them is light. You can't take them into a box, change their mass, change their temperature, or whatever. You don't have a lab to test the star. All you can do is gather the light that gets to you and get as much information from it as you possibly can. What we do in spectroscopy is we take that light, run it to a prism, the same thing you would use to create a rainbow from the sunlight, and that splits its energy levels up into this nice bar in which you have the lower energies here and the higher energies here. Now, this looks very nice, but this is hard to work with, so usually we actually plot it in a plot like this, which we have wavelength going to the right, so this is going to lower energies or longer wavelengths, and brightness going up, and then you see a profile like this. So this brightness gets plotted here, this brightness gets plotted there, and so on. And these dips you see, these black lines in the spectra, but these dips in the brightness plots are actually the important part. They sound like an annoyance in the, if you look at it like this, but they're the important part because they are created by specific elements absorbing light at very specific wavelengths. Remember when I said that you have these discrete energy levels and it can only really absorb light at these specific wavelengths? Well, this is important now because they are at these specific wavelengths, the state of these elements, let's say it's hotter, and some of the elements get excited just by bouncing around against other atoms, and gets excited to the second level. Now this atom can no longer do the 1 to 3 transition. It can no longer absorb that photon from before, but it can absorb the 2 to 3 transition, which this one, at the moment at least, cannot. And this is because the region where this thing is hotter. So based on the relative strength of this transition and this transition, we can figure out the temperature and the density very locally in the star. If it gets even hotter, let's say this atom gets moved to an even hotter place or for some reason it heats up, it can get that bad that the electron escapes entirely. It gets so much energy by bumping around that it escapes, and that's what we call it's ionized now. It's lost its electron. For hydrogen, this is particularly annoying because you lose everything. There's no longer any line transitions happening here at all. For things with multiple electrons, such as helium or iron, this is less of an issue because they just have the other electrons moving around and you can still see them quite clearly. So we now have our starlight, we have our spectra we want to look at, but the efficient way to work ahead now is by comparing this real starlight to, well, fake stars, fake spectra, synthetic spectra, which we create in a computer. For this, we use a code called FastWind. It is a 1D stellar wind and atmosphere code. And basically what it does is it creates a fake star, which looks like this. Basically, it is just a density profile and a temperature profile, a velocity profile. It calculates what spectra it expects to be, and then you can compare those to observations. One of the big assumptions we make here is that the star is 1D, which means that any line I take from the star from here to here needs to be the exact same as any other line, which means it needs to be axisymmetric. The sphere needs to be a perfect sphere, pretty much. It needs to be equal in each direction. Well, each direction that way, at least. That doesn't necessarily need to be true. Another disadvantage of doing it in 1D is that a lot of the processes we're interested, such as clumping, are inherently 2D or 3D, they're multi-D. Because to have clumping, you need to have material moving to the side of other material, bumping into other material, and in 1D, that just can't happen. You have to have a monotonic velocity profile. Velocity only can go up. It cannot stop briefly to let something bump into it. So that means that you need to add a lot of parameters. You need to parameterize all these different physical processes you're interested in, meaning that even though computationally it's more efficient to do it in 1D than 3D, and a lot of other reasons it's also easier, you end up with a lot of extra parameters. In total, we want to constrain 18 parameters at the same time, which is a lot of parameters. 7 of them are stellar. This includes temperature, mass, rotation, and the chemical makeup. 9 of them are the wind parameters, which include mass, the velocity profile, which takes 3 parameters on its own, and the clumping, which take 5. And then 2 X-ray parameters. This is just extra parameters for in the case there is X-rays present in the star, we want to model those as well, and we need to add those. So here is an example of how we actually work with these lines and observations. First thing you do when you get an observation is you actually take a look at the lines. Here in white is the observational data. So we got a star in, we got a spectra in, and we see this line and this line. This is a helium-1 line, meaning it is formed by neutral helium, and this is a helium-2 line, meaning it is formed by singly ionized helium. So that means one of its electrons has left because it's too hot. And then you make a first guess. And my first guess here was 25,000 Kelvin of a model. I look at what the spectra produces, what the model produces in terms of spectra, and we see, okay, the helium-1 line is a bit too strong. There's too much neutral helium in my fake star compared to the real star. And helium-2, I have none. My star does not produce helium-2 at all, my fake star. My real star does, which means that my fake star needs to become hotter to become more like the real star. We do that, we up the temperature by quite a bit, and look at that, we got helium-2. We upped it to, I think this is 40,000 Kelvin, and now we see that, okay, helium-2 is present, good. Now we look at helium-1, uh-oh. We have lost a lot of our helium-1 because it has been converted into helium-2. So we need to now optimize this a bit, find the correct temperature at which we both have the helium-2 and the helium-1 present in the correct amount, and that is eventually you get there. And here the helium-2 looks happy, the helium-1 looks fine, we're good. This is the correct temperature. Now you can do this for each of these 18 parameters over and over again by eye. because all of these parameters have a slightly different impact on different parameters. So you do them one by one by one by one until you're ready. And one of the advantages of doing it this way is you don't actually need that many models. Usually a couple of models are enough to get a good constraint on each of the parameters. One of the issues is that once you run a model, you look, you say, it needs to be hotter, the whole model needs to converge again. So you put in a new model, press enter, wait for that thing to run and give you the actual output. In FastWind, this takes about 45 minutes. So every time you press enter, every time you make a new guess, you're waiting 45 minutes. Other codes on the market, such as CMFGen and Power, take about 2 hours to, depending, a couple days. Then you're waiting a long time to test what the hell is actually the real temperature. But you don't need that many models. That's the big advantage. And another advantage is you get a real hands-on experience with what the actual parameters do in your star. One of the disadvantages is that at the end you have a spectra that you have determined to be the best based on your eyesight, based on what you think the best one is, which is very hard to compare to anybody else doing other work, because you don't have a metric to compare to other people's metric. On top of that, getting actual error bars out from this is extremely hard, because you have derived it with so few models that you can't get a statistical error bar out. These error bars need to come from your experience from working with the code and with the data, which is also something that, one, takes a long time to train, and two, can differ from person to person depending on how optimistic you are. What we did instead is we just ran a whole lot of models. We just ran tens of thousands of models and compared them to the data, and then we found the best one. Well, it's a bit more complicated than that. We optimized it in various ways to make sure that we quickly get to the correct model, because otherwise 10,000 models would never be enough. We just run a whole lot of models. The disadvantage is you have a lot of computation time all of a sudden. You're not computing a couple parameters each time, but you're a couple of models for each parameter, but you're computing thousands. The advantage is that you can very easily parallelize this. You just put a model on each computer, basically, on hundreds of computers at the same time in a supercomputer, and you get this out relatively quick within like a day or so. And the big advantage now is that you can actually get the error margins out quite well, because you have a whole statistic to compare it to. So what does it look like in the end? When you have the full output there, it looks something like this. When we're done, we've computed all our models. You get the fits over here. In white is the data. In green is the best fit. And then the green shaded region is the 1 sigma uncertainty. And here is 5 line windows, as we call them, with multiple lines each. But in reality, I have about 40 of these line windows that need to be fitted at the same time. They all look very different. They all have different dependencies on different parameters, and it works quite well. Now, another nice thing you get out is for each parameter, here I show 2, for each parameter you get a box like this. On the y-axis, you have the quality of the fit, meaning how good the model is. On the x-axis, you get the specific parameter you were interested in. Here it's temperature and mass loss rate. Each dot in these plots is a model, one of the thousands of models we ran. And depending on how high it is, means how good it is. Now, each dot, I know in this plot at least, I know what the effective temperature is, but all of these dots that are not as good as the best model in the end have different masses, different mass loss rates, different rotations, and stuff like that. But in the end, because you have this distribution, you can find your best model and then statistically just get your error margin out like this. And that gives you very easy ways to compare to other people, because you have a value connected to your quality of fit. And if somebody does something different, include some lines, not include some other lines, it's very easy to compare if we have a better fit or a worse fit. I have used this method on objects, not in our galaxy, but in the Magellanic Clouds. The Magellanic Clouds are 2 dwarf galaxies that are gravitationally bound to the galaxy, but not actually a part of the galaxy. We have the Large Magellanic Cloud and the Small Magellanic Cloud, and the interesting thing about them is that they have different makeup. They have a different metallicity. The amount of material that is present in them is different from the galaxy, meaning that it's interesting to see how the different things present in the star actually affect the star. For instance, the Large Magellanic Cloud has a metallicity, as we call it, of half that of the sun, meaning that its iron content is half that of the sun. And remember, iron is very important for this line driving. The Small Magellanic Cloud has even less of these metals. It has 1/5 of the metallicity of the sun. We like to compare things to the sun in general, but specifically for metallicity, it is because that's the star we know best. That's the easiest star for us to study. Doesn't mean it's easy, but it's easier than all the stars that are very far away. We know a lot more about it. So now let's go over the results. So I looked at 41 stars in the LMC and SMC. 17 of them are in the LMC, 24 of them in the SMC. Here they're plotted on an HRD. So again, effective temperature going down to the right, luminosity going up in log space. So this star has a luminosity 1 million times that of the sun. The temperature range is about 35,000 to 12,000-ish Kelvin. This is mostly in the B-star regime, with some outliers that turned out to be in the O-star regime, which is above 30,000. And the masses I get out is from 15 solar masses to 75 solar masses. Now, these gray lines I plotted here are evolutionary models, so how we think a star with this specific initial mass should evolve, to give you a vague idea of where in the HRD we are, which masses we're talking about here. So the first thing we wanted to look at was the mass loss rate. And when you just plot the mass loss rate of the SMC and LMC stars of the effective temperature, again, effective temperature going down, mass loss rate here on the y-axis, again, in logarithmic space, meaning that this one is losing enough mass to lose 1 solar mass worth of material in 1,000,000 years. You do not see a bump, because this was what we were comparing to, right? This was the thing we wanted to see. Which one of these three is the one we are seeing here? And I do not see a bump. So does that mean we're done? Well, I mean, not really, because it's very hard for me to compare real data to these models. Because in these models, they were able to keep the luminosity and mass of each star the same. They were only varying the temperature. While in the real stars, I cannot choose that. If I look at a star, I just get the luminosity and mass of that star. I don't get to pick what it is. So it could be that all of these stars at the low end of the temperature regime are also stars with very low luminosity or a very high mass, reducing the mass loss rate. So what we do instead is we take the values we know of our stars, the mass, the luminosity, the temperature, we plug them into the prescription, and that gives us a prediction of the mass loss rate based on those prescriptions. If you divide that by the mass loss rate we found, you get a plot that looks like this. Here I split it out, the LMC and the SMC, and I'm only showing you 2 of the prescriptions, the Vink and Bjorklund prescription. What does this plot tell you? Well, on the y-axis, it gives you the prescription over empirical value, again in log space, meaning that at 0, the 2 models agree. That means that if you want the model, if the model is good, all models, all stars here, all dots would fall on this green line in the middle. If it's above that green line, your prescription is overestimating, and if it's below the green line, it is underestimating. Because it's in log space, if you see one at like a factor 1, that means 10 to the power 1, it is overestimating by a factor 10. If it's at 10 to the power 2, it's overestimating by a factor 100. What we see here is also the dashed lines show you the average of the prescription, the average offset of the prescription. So for instance, for the Bjorklund rates here, its average offset over the entire range is about a factor 2. When we look at the Vink rate, the one with the jump, we see that in the beginning, it's overestimating by about a factor 2 or 3 until we hit the bistability jump, this discontinuity in mass loss rate. It jumps up, and its mass loss rate now, its average is about 40 times overestimating, and up to 100. There are some stars here at 100. So that means that the shape the bistability jump predicts is not real. Otherwise, we would see a constant offset as we see with the Bjorklund rates. Well, except for this outlier, but like we would see a constant offset, but we don't see that. We see this discontinuity in the offset, meaning that the discontinuity in the model can't be real. Now, I didn't go over the SMC there for the simple reason that we would get the same conclusion there, but I do want to compare the Bjorklund rates and the Kritička rates here, because they're a lot similar, a lot more similar. They have some differences in them. What we see, as I mentioned before, in the Bjorklund rates is a very constant offset by a factor 2. For the Kritička rates in the LMC, we see that they're actually, on average, bang on. They're like 0.98, almost 1, perfect. The problem with them, though, is that they're sometimes underestimating, sometimes overestimating. So although the average seems to work out, maybe the shape they predict isn't quite correct. If we look at the SMC and SET, we see the Bjorklund rates and the Kritička rates again. Now the Bjorklund rates are underestimating by a factor 8, which is a lot bigger, and the Kritička rates are underestimating by a factor 2 now, which is more than it was before. And there are no longer any stars overestimating, or barely any stars overestimating. We also see in the cool temperature range, which we didn't have a lot of data for here, it is underestimating by a lot for both of them. There seems to be a too strong decrease of the prescriptions with temperature, and there seems to be a too strong decrease from LMC to SMC. So the metallicity dependence is too strong. Okay, that was it for the mass loss rates. Now I want to move to clumping. How is the wind structured? As I mentioned before, there's these 2 factors that I talked about at the beginning, the interclump factor, the clumping factor, telling you how dense or underdense the material is. If we look at the interclump factor here, again, shown on effective temperature going down, and here in log space, meaning that here the interclump factor, so the material in the non-dense regions is about the same as average. Here it's 10% and so on, and goes down. What we see is a large uncertainties, large scatter. This is not good. We were hoping to see something nicer than this, something way more correlated with something. We didn't find that. But something interesting we did find is that on average, we expected stars to be mostly in this bottom part of the plot, like in between 1 and 10%, right? But we see that most of the models instead find the best fit for way up there, at like 30, 40, 50% plus. So we took the average of both the LMC and the SMC to see how dense this interclump is on average at least, and we found for both of them independently that the 40% of the wind mass is in these interclumps, which is a lot higher than the 1 to 10% we started out with. So there seems to be something wrong with our idea of this two-component medium in which you have very high dense material, then a whole lot of nothing, and then very low dense material that is basically void. There's basically nothing there. So what I did is I looked at some 2D models. This is a model from Florian Driessen, who actually did 2D models to study the clumping, and this is for LMC, SMC, LMC galaxy, and these plots are very nice. They show you the high density regions in red and low density regions in blue. And you see that you get these clumping out naturally in these 2D models, so that is good. But then I wanted to go a step further, and I was like, okay, well, he went a step further. I didn't do anything here. He made this plot, which is very, very useful for me, because it shows on each radial distance from the star what the likely density is you're going to find. So this is basically the wind flowing outwards, and the darkness here, how darker the color is, shows you what the likeliest to find that density. And what we do not see is a two-component medium. Instead, what we see is one nice Gaussian, pretty much. The dashed line here, by the way, is the average, so everything below this would be considered interclump, everything above this would be considered clump. This is a bit less clear now that there's not a two-component medium, but that would be the nomenclature we would use in the old way of thinking about it. But that means that what I find is not necessarily a problem with the stars itself or with our method of fitting, but is a problem with the models we use. The models we use do not describe reality, and if you use the wrong model to fit something, it's always going to give you large scatter, always going to give you large uncertainties. So it seems like we just need to change the way we induce this clumping in our 1D models by quite a bit. Then finally, I want to end up with the metallicity effects. So as I mentioned before, I looked at the SMC, LMC. The biggest difference between the two is that their metallicity, the amount of heavy material, is different between them. LMC is about half that of the Sun, SMC is about 20% that of the Sun. And the idea would be, well, more iron is present in the LMC than the SMC. The sail, so to say, is bigger to catch the material, so you should see higher winds, higher mass loss rates for these LMC stars. And in the O star, that seems to be somewhat true. Here, the blue is the SMC, and the yellow-orangish is the LMC, and you see some differential. Now, it's still somewhat cluttered. There's some LMC here higher and lower than the SMC, but they are somewhat separated. For the B stars, on the other hand, we find that they pretty much completely overlap. There is no real difference between the mass loss rate on SMC B stars and LMC B stars, at least as I found. And this is strange because this entire explanation, the entire explanation of how a stellar radiation-driven wind works is very dependent on this content of iron. And, well, it doesn't seem to be for the B stars, and that is weird. I do not have an actual, full theoretical explanation of why that happens, but there is one, I'm going to call it mass loss calculator, because it's a bit different from the prescriptions we were talking about before, but it's very similar in function. This is a calculator called LIME, in which you put in mass, luminosity, temperature, and metallicity, and you get out a mass loss rate. And if you look for 20,000 Kelvin stars, so these are B stars, look at the mass loss rate, how it changes with luminosity, and then the color here shows the metallicity of the star. There's very little difference in the actual mass loss rate between solar metallicity at yellow and all the way down there at 1% metallicity. Keep in mind that the SMC and LMC are located here and here, so it's no wonder we don't see a difference within our error margins, because there's barely any difference here at all. For the O stars, on the other hand, the scatter seems to be a lot bigger. The O stars seem to have a lot bigger difference based on metallicity. So that can give us some hint on where to look, why we are misunderstanding or not interpreting this completely correct. So what did I learn over 4 years of this PhD? I have shown a lot of things that are wrong or we need to change. One of them is the bistability jump. The bistability jump is not present. It is not present in the SMC, it's not present in the LMC. Other people studied the galaxy at the same time I was studying the SMC and the LMC. They didn't see it in the galaxy either. It is just not there. Empirically, we cannot retrieve it. This matters a lot for understanding of how massive winds work, but it could also change the way we think about evolutionary models, because if you use this prescription or this prescription, as I showed, you get a completely different star out in the end. We also learned that the way we thought about the wind, the way we think the wind is shaped, formed, what its density structure is like, is completely, well, was off. We thought it looked something like this, in which you have high-density clouds, high-density regions, followed up by basically nothing. It is void. To the point that a lot of the codes used to do stellar analysis actually assumed that was the case and just ignored the void parts altogether. They didn't bother modeling it, because if there's no mass there, what's the point in trying to model it? It's more like this, it turns out, in which you see some high-density regions, some low-density regions, but it never comes a complete, like, clear cloud deck. There is always some material in there, which is very different from what we thought before. Then finally, for B stars, metallicity seems to have no impact. For O stars, there seems to be at least some impact. Why that is, I don't really know yet. We have some theoretical models that at least give us a hint, or theoretical model calculators that seem to show the same behavior, but why they show up in that calculator, we don't really fully understand, I'm afraid. Thank you for listening. I hope it was somewhat interesting, and yeah, happy to take any questions.
Thank you. We will start first with the questions by Paul Crowther from University of Sheffield, UK.
Go a little bit. Olivier, thank you very much for your, excuse me. I very much enjoyed reading your thesis. It's a very impressive piece of work. I guess I have a couple of questions. The first, to follow up on what you talked about in terms of the line driving in the stars. It's clear from studies of the O stars in the two galaxies that there is this empirical difference, quite a significant difference between the wind strengths between O stars and the LMC and SMC. And yet you found more or less the same strength of winds in the B stars in the two galaxies. And yet when one looks at the observations in the ultraviolet in terms of the P Cygni lines and the optical in terms of H alpha, one does kind of see a difference between the wind strengths of those two galaxies on average. So do you have any more thoughts about how one might, are there any issues in terms of reconciling that empirical information and your results which show no offset?
Yes. So this is a very similar question than the question you asked in my internal defense, right?
Yes.
So, and I very much agreed with you. I was like, there needs to be something in these lines that we can look at. So I actually plotted some of these lines, very ugly, very last minute. They're in here somewhere, I hope. Yes, here they are. So what I did is, you said me like, okay, we have LMC and SMC, and the H alpha line, which is the main line we use to look at mass loss rate, shows higher peaks for the LMC than the SMC on average at around the same temperature. So I just looked at the data I had. I chose the closest mass loss rate temperature stars I had in the LMC and SMC. SMC here in blue, LMC here in red. And I must kind of disagree with your initial setup of the question, because if I look at this, the blue is SMC, it has a higher peak, which means higher mass loss rate. That is contingent to what I say. Here as well, here as well. Now, it's not true for all of them, of course. We have some cases in which the LMC shows a much higher peak. And I don't know which star this is exactly, I would have to look it up. But like on average, yes, some of them are higher, but I wouldn't say it's a consistent thing that the H alpha lines are always higher, have these higher peaks in the LMC and the SMC. Maybe in general, if you do not get close stars in temperature, that might be true, but these are just based on the closest stars in like both coordinates of mass loss rate and temperature, the closest two stars I could find. And I found 6, and this is just the 6 closest, so I didn't like monitor this in any way to make it look like I'm correct. These are just the 6 closest I have. So I agree with your point for the P Cygni lines, because there it definitely still holds, but there it could be an effect of just a lower amount of carbon, nitrogen, oxygen, because that is the lines we see there. But in the H alpha, I must say that I don't fully agree with the first setup of the point.
Okay, thanks for those. And then you also in your presentation showed how we go about measuring temperatures. And you gave a good example of the helium lines where you were too cool, which underestimated one of the ions, and then vice versa. Now for O stars, it's often easier because you have strong helium lines. For B stars, which is the bulk of your sample, you have to rely on much weaker silicon lines, and especially in the SMC, where the lines are really weak.
Yes.
So have you any thoughts on how one might verify your inferred preferred temperatures from an alternate thing that's other than the the weak lines that you have to work with?
Yes. So what the example I gave for the helium-1 and helium-2 lines is kind of cheating because they were for O stars and not B stars. And B stars we need to rely on other elements, and they are a lot less strong. And indeed, definitely in the SMC, where these elements are even weaker, we run into some issues. The error margins, or the certainty we have on the temperature, becomes rather large. It's hard to verify these things, and the decision to include or exclude certain lines seem to impact the eventual mass loss rate quite a bit. This is true. A way to verify this would be by looking at the Balmer jump, which is a jump due to basically hydrogen excitation, which is a big peak in the spectrum of the star, and the height of that peak for specifically B stars is very much related to the temperature. So you could try and use that instead as well to get a temperature out. I think that's what you're referring to. Yes.
Have you done that, or?
I have not.
yeah, but you will.
I will.
Yeah.
I will.
And my final question is on some of your preliminary work, which you weren't able to present today, but you did in your thesis, which is use of neural networks to speed up the efficiency of which one can analyze a large number of stars. And the example you gave for an LMC O star looked very promising. Have you any more thoughts about whether any unexpected challenges one might have if one tries to approach this from optical observations for a large sample with a neural network approach?
Yeah, so I think I have slides for this as well, but I think they might be, they're here-ish. So together with a student who's here, Anya is right there, I worked on producing neural networks to kind of get rid of fast-wind altogether, basically make an emulator of fast-wind because it takes quite a long time for each model to be computed. And if we compute thousands of models, this takes a long time. If you want to do this faster, how do we do this faster? Well, we make something that fakes fast-wind's results out and does that almost instantly. And so what we did is we did that for O stars specifically because they're easier. I know, a lot of different ways, but mostly temperature. And we had some first results and they showed very promising. Now, comparing to results when you use fast-wind compared to neural network to fit actual stars. Now, the challenges, I can't really predict all of them. I think one of the big challenges will be convincing people that this neural network is good enough. I think that is like one of the main things, because the main thing I would say is make plots like this, in which you compare the offset of your neural network with the fast-wind, the actual code, and then see how big the error gets. And as long as the error remains small for like almost all of the models, I would be very content with that. And then, of course, test an actual fitting routine, check you get the correct values out. The biggest issue I see maybe is when we move from O-star regime, like if you want to do large samples, which also include B stars, luckily/sadly, you need to expand this regime from only O stars to also do B stars. The problem there could be that fast-wind is a lot less reliable, so to say. It is a lot more prone to not converging in the B star regime. This is an issue I had to work around with through my entire PhD, basically. I did small optimizations to make it more stable in the B star regime. There's a lot more to be done there to make it more stable in the B star regime. But that means that if you're building a training set to train your neural network, which can include hundreds of thousands of models, you are going to have to overrun a bunch of models that you're never going to be able to use because they didn't converge, meaning that your computation time explodes, maybe. There's probably ways around this as well, but I think getting fast-wind to be more stable in that regime or tuning the parameter ranges in which we actually want to have our data set could hopefully resolve that a bit. Now, I haven't tested this as much in the B-star regime yet, so I don't know how bad it will actually be, but from my GA fitting, so using these thousands of models, I know that in the B-star regime, there tends to be about like 30% of the models fail. If you even go even cooler, it is like close to 50% that fail. So then you need to run double the amount of models, which means instead of running them for a month, you're running 2 months worth of computation time, which is significant.
Okay, thank you very much. Congratulations again.
Okay, you can sit down. So Olivier, congratulations. I was present, of course, to your private defense. I'm here today. I enjoyed your presentation. As you know, the way I ended up being here was a little bit also sad because I'm replacing a colleague who is no longer with us. And but okay, I enjoyed the process. I have no background in astronomy, and well, I enjoyed reading your thesis, and I learned quite a bit. So we went through your private defense. You had a lot of technical questions and so on. I think you did very well. And today I would like to ask a couple of a bit more general questions. And in fact, I'm asking questions, and now I'm bringing you to my perspective and more, because, well, you wanted me to be here, and okay, so that's the price you have to pay. And so my background is statistical physics, you know, and one of the things we learn in statistical physics, in quantum statistical mechanics, actually, is this black body radiation spectrum and so on. And okay, so I teach it to the students. I taught that for many years. And yeah, it's a very idealized system, you know. There you have a cavity, you have radiation, and so on. And but when I come to concrete example, I understood that in astronomy is actually many stars, they show a black body-like spectrum to quite a good degree of agreements. Now, if I now think the ideal world of this black body radiation towards, and I think about the real star with all these processes and so on. So can you explain us why is that this black body spectrum works, say, decently well in this?
So what you would need for a black body spectrum is that everything is nicely one temperature, right? That's the basic idea. It needs to be all homogenized in one nice black body where only one thing escapes, and that's the light. So I guess the reason we see somewhat black body spectrum with, of course, the additional things such as the Balmer jump, which is quite a big derivation, like offset from this, is because the star itself, definitely if you go to more compact stars, not the supergiants I talked about here, but the more compact stars, is because the actual surface of the star, beyond, if you go a bit more internally into the surface, everything is very densely knitted together, collisions dominate. So everything is just constantly colliding, and it's only in a very small outer layer where all these additional effects, or in the wind in this case, but if you have a star with less wind effects, it's going to change as well. It's only in this very outer layer where all these properties, actually all these processes take place. And that is, I think, why we see a quite nice black body curve, and we can even use that curve to derive things such as temperature of our stars out of it, roughly.
Okay, so massive stars compared to non-massive stars, do they have the same type of deviations in this black body radiation, or can you see it more in... Because what you are saying actually is that because there are a lot of internal collisions and so on, that there is equilibrations, and then we can think about this, you know, this black body equilibrium spectrum is quite well represented. But do you see a difference in massive versus non-massive stars, in deviations from black body, or?
In deviations from black body. So I have not actually looked at that directly at any point, but my assumption would be that the more fluffy your star is, so to say, so you have, I looked at supergiants, right? So they are very extended. Their outer layers are very extended because there's a lot of radiation that's pushing it. It's very fluffy. The outer layers are actually not that dense. And in those cases, we need to get away from what we call LTE, I guess, so local thermal equilibrium. It is now no longer, the star itself is no longer, or that region of the star is no longer defined by its local properties only, so its temperature, its density, and so on, but it's also defined by the radiation coming in from outside of it, from other regions. That is part of what makes massive stars and these massive star winds a lot more complicated. So it assume for those stars for which the luminosity, rather than, and that goes with mass, of course, the luminosity is a lot higher. You see these higher luminosity classes, such as giants, supergiants, bright giants. There we would see a bigger offset than for the very condensed stars, such as dwarfs and stuff like that, would be my assumption.
Yeah, thank you. It's nice you mentioned LTE, because my second question is LTE versus NLTE, no? Yeah. Also, this is... it's very close to my heart, statistical physics. We work a lot about non-equilibrium thermodynamics and so on. So how do you decide when something is LTE or there is non-local? So do you see it from your model? The model does not fit what you see, and then you say, well, we have to go through non-local thermal equilibrium, or is it something that you know it beforehand and you know you're sure, no, we have to use here the non-local equilibrium?
So based on what I said before, the luminosity, how fluffy sort of you think the star is, that could inform you if you think LTE or non-LTE is needed. But I think it is even in a Kudrytski paper at some point, he mentions that if you want to be sure that you don't need NLTE, you first need to try NLTE and see if it differs greatly. Okay. I think I have a plot of Kudrytski from that paper or another paper in here somewhere. I just pasted these all at the end, the back, but they're in there somewhere. I'm sure of it. Here we go. So this is, I don't remember where, so this is apparently not from Kudrytski, but from Prisbilla. And what you see here is basically how the population levels of hydrogen, I'm pretty sure, differ for a specific star. This is a B star, so that works out nice, a B8 star. How they differ NLTE to LTE for the star. So they calculated first an LTE, then an LTE, and what they saw is based on the depth of the star, so this side is deeper into the star, this side is into the wind, you can see that certain population levels start to have an underestimation compared to LTE and an overestimation, and this can be relatively big, because again, we love log scale, this is on log scale, so here we're looking at like factor 2 or 3, something like that. So this is actually the only way to be 100% sure if you need NLTE or LTE is just by running both and seeing how big the difference is. And you can estimate based on how fluffy you expect the star to be if you need it or not.
Okay, thank you very much. Also related to a bit to my field, which is also involves biology. At some point, you mentioned that you are working with a genetic algorithm, and I was wondering if you can explain us, the audience, you know, genetic makes me think about genes and DNA, and so how is the, what's the idea? And why is it called genetic, actually?
Yeah, so I first wanted to explain this because it's actually a very visual way of explaining it, but then I figured I wouldn't because it's actually mostly the work of Sarah Brands, who's another, well, used to be PhD student, now she's just a doctor in Amsterdam. So basically how the idea works, I told you guys that we run just a whole lot of models. We run tens of thousands, well, not tens of thousands, we run thousands of models, and we just look at what the best one is. That is a bit of a simplified way of explaining it, because that in reality, if you'd really just do it randomly, it would take way more than 10,000 models. What we do instead is we start with a random distribution of models, about 100, and then we compute the Fastweb models. We compare those Fastweb models to the actual spectra, and then we can rank them. So the best fitting ones get on top, the poorest fitting ones go to the bottom, and then we use the better fitting ones, and we do a step called reproduction, in which you take two of the models that look fine, looked good, you take randomly one of the two parameters for all of them, then you allow for mutations. So now you have a new model, you have two new models, right? But then you allow for mutations. This means that each parameter separately can jump to a different value based on a Gaussian, so you have randomness to it, and then you do this on a loop until you're happy with your results. So now you have a new generation of models, and you go again and again and again. And in about 50 to 70 generations, and because each generation is about 100 models, you need about 5,000 to 7,000 models to get to a good result. One of the nice things about this is that you very quickly hone in the region that you know is fitting well, so you're not wasting your time randomly in parameter spaces that you know are gonna be horrible anyway. And the mutations allow for random steps so you can get out of local minima. One of the issues you have if you have 18 parameters is that usually if you could imagine your chi-squared landscape or the goodness of fit landscape looks very hilly and bobbly, and there's a lot of local minima. So these random mutations allow you to get out of these local minima. Now the issue, not really, well, kind of the issue, is you're never guaranteed to find the global minima. Right, this is a random approach. If you do these random types of approach, you're never really sure if you found the local minima. You're just the global minima, so the actual best fit. You're just sure that you found a good fit in the end. And the only way to be sure that you actually found the best overall fit is by covering the entire parameter space, which is computationally not really feasible.
Okay, thanks a lot. Thank you for your answers. And now I have to give the microphone to somebody, but. Thank you.
So I will give the word now to supervisors. Yeah, Jan.
Thanks a lot, Olivier. We have, of course, discussed more than enough. No, that was a joke. Can never be enough discussion. So I'm not going to ask you so much about your work today, because that we have covered. But of course, you have already hinted that actually you have done a lot of extra work in addition to what you presented here today, which are your main results, the bulk, so to say, but the genetic algorithm, we had the turbulent pressure. You have also worked together with your other group on other objects, post-AGB stars, published there as well. So there's a lot of stuff there. And now I'm just a little concerned, since, you know, you're sort of leaving me a little bit now. So what am I going to do now with what are we going to do now with particularly with the turbulent pressure project and well, the GA, the neural network project? What is our plan?
What is our plan? Wow. Well, I'm here still for like 2 months, so I can do some stuff, hopefully, for the turbulent pressure project. So, I mean, I don't know how to briefly say this. At some point, I introduced turbulent pressure in Boston. That's what Eunice mentioning, and it turns out that you can correct mass discrepancies we see with observations and what we think is reality. So that is a project that is still very much ongoing, indeed. I think we are definitely, after I wrote it all down, we are closer than I thought to actually writing it up and sending it to the peers to review. So I think I could do that, hopefully, in the next month and 2. For the neural networks, I think there's a little bit more work, to be honest, for a number of reasons. One is because I want to make sure that we're covering all our bases, to make sure that people who use it know all the quirks, know everything we think is important, and it's a full analysis of this neural network. But luckily, Anja, who worked on them, is starting a PhD in Amsterdam, so she can continue that work mostly without me doing anything, so that's going to be fine, I think. So for the turbulent pressure things, I want to finish that off, hopefully myself in the next couple of months. For the neural network part, I think Anja is more than capable of carrying that forward, if she wants to. But you have to convince her then, I guess.
We work on that together, huh? Yeah, that's great. No. So no, I don't have any further questions. So congratulations very much. You should be proud.
Thanks.
If I can comment, you have learned to delegate. That's a very important quality. So Alex, I will give you the word.
Okay. I've also had the opportunity to ask you questions for 4 years, right? For most of that time, we would meet like every week,
Yes,
and talk for an hour and a half or 2. So I've asked already thousands of questions. So I'll only ask one question more, my final question. You were explaining that you have this prescription in your models that tells you how the clumps look like and the medium in between the clumps. Yeah. And then you showed a figure where you compared this with models by Dr. Driessen. Yeah. You explained completely different. Yeah.
Yep.
What you find and what he finds is not the same. And so it flashed through my mind that there are 3 possibilities. Yeah. One is that there's something wrong with your way of describing the clumping. That's one possibility.
Yeah.
The other possibility is there's something wrong with the models of Dr. Driessen. Yeah. That's possibility 2. Or option 3 is both you and Dr. Driessen are wrong. Yeah?
Yeah.
But you immediately concluded there's something wrong with the way I prescribe these clumps. So why is that your conclusion?
So
Why do you, let's say, believe more in the models of Dr. Driessen, apparently?
I mean, Dr. Driessen has a great track record of stuff, so that's part 1, I guess.
Very diplomatic, yes.
But no, the reason I am quite ready to dismiss the prescription we use, because you say my prescription, but it's a prescription that actually Yoon started out with doing. So it's easier to dismiss. No, so what we found is that one of the expectations this prescription had from the get-go was this low interclump medium. And we tried in a lot of ways to subdue the interclump medium in our results, because we thought we were doing something wrong in the beginning, right? We thought like, okay, we see this high interclump medium, this cannot actually be, theory tells us it shouldn't. So we tried a couple of things to solve it, and whatever we did, it instead of accepted that we really forced it not to go up, it would keep wanting to go up. So we said, like, okay, there's something in these stars, something in these spectra, and we can actually like look at some of the lines that get influenced by it that wants them to get pushed up. It doesn't like to be at these low values. So that shows me that the prescription I'm using is kind of fighting against reality, and that you also see in the very large error bars and very large scatter we have. And that's not just what I find, that's what other people who work on this, like Frank and Sarah, also find. They find these very large scatter bars, very large error bars, very large scatter on their interclump density, their clumping factor less so, but their velocity filling factor as well. They see this all the time. And this, because we find this high interclump density, it actually pushes us towards what Florian finds as well. So I think my results and what Florian is showing in numerical 2D models are actually very close together. We are not showing a different thing. I am showing something does not work and wants to push towards something, and that something seems to be very close to what Florian is proposing. So I think we're actually very close to saying the same thing. I'm just saying what I have right now does not work. What Florian has is interesting and seems to be towards where I want to go for it to work. So I think option 3, we're both wrong, is in a way more likely because we're saying the same thing. So,
okay. Thank you. Thank you.
Thank you, Alex. I think it's always wise to say we are on the proper track.
yes. Yeah. Process.
I was planning to sit there, but Olivier, what the progress? I remember the 9 months presentation. The first year you've been working with the GA for 9 months, and you were struggling to wrap your head around those 14 or 17 parameters. Yeah. And now today you've shown that you're just juggling between all those parameters, and you even want to throw a few more dimensions. So
true, yeah.
So what a progress. All right, we've been talking a lot about stellar winds. Can you go to slide 31?
I have no idea what's on slide 31.
I want to talk about stellar evolution.
Yes, of course.
What is the question I'm going to ask?
If I can make a guess, you're going to ask, hey, wait a minute, this is the Hertzsprung gap. Why are there so many stars here?
Exactly, that's good. That's how you become a fully trained researcher, that you are able to ask yourself your own questions. Can you also give yourself your own answers?
So what for the audience, what we see here is this is stellar evolution, and this looks like a nice gray line, but what is kind of deceiving here is that the time it spends over here and the time it spends over here is not equal. We expect this horizontal line over here only to take 10,000 years-ish, while this bit here takes millions of years. So we expect to find many stars here, very few stars here. What we're seeing instead is no stars here, a whole lot of stars here. That's a bit weird. So one of the solutions to this, and I think that's why I got it asked, because I didn't mention it at all during my talk, kind of on purpose, is binaries. Stars can form, and massive stars actually oftentimes form in these pairs, in which they have a companion of some sort of mass, and they orbit around each other, and in a lot of those cases, they interact. And if you make, these are single star treks, so they are assumed to have no partner. If you make binary star treks, they can actually come back to this region due to interaction and stuff like that, meaning that probably a lot of these stars, if not the majority of them, because they're O and B stars, so they should all be binaries, like, what is it, 70 to 100% of them should be binaries, are probably binaries. Now, I can concede that, and I will add to it that I don't think for what I did it matters if they're single or binary, except if it influences the spectra. If they are both influencing the spectra in some way, then I'm getting weird results. And I think I am seeing that in some of the helium abundances I get very low helium abundances, which might point to there being a secondary messing up my signal a bit. But for the wind part, as long as there is not like some huge structural change I cannot fathom, the same ID remains. We have a star with a certain temperature, with a certain luminosity, and a certain mass. And if I get those correct, because they're not influencing, the binarity is not influencing the spectra, my base results should be more or less the same, I think.
But if those stars are living there for a reasonable amount of time, doesn't that mean that the stellar structure that you're assuming is wrong? Because if it was that correct stellar structure, they should evolve fast.
Yes, But in the models I run, I only care about this very outer layer. Like Fastwind only models into like an eeny beeny bit compared to what these models do, which go all the way to the core, an eeny beeny bit into the star. We care about like the outer layer and then the wind. And in that region, as long as it's still just a star with a certain luminosity, maybe some turbulence going on there, it will be more or less the same. Now, will there be some consequences evolutionary ways? Of course, there definitely will be. But I tried as much as possible to stay away from making statements on what the actual evolutionary type of star these are, because this is indeed awkward, so might as well not mention it, I guess.
All right. We still have a bit of time. One more. This is the last one, promise. You mentioned a few times that you can disagree or disprove theories, like the B-stability jump, for example. Seems as it's not present in the data, but you stay away quite a different occasion of answering the answer why.
Yeah.
So why is the B-stability jump not present? Why is physics telling us that that model is different than those models?
So this is, I think, a pretty technical, requires a relatively technical answer. So what you're basically asking, or the way I see it, is these models all are based on the same physical idea I started the first 20-ish slides with, trying to convey how they actually launch these winds and how the stars are formed and stuff, or like how they work internally. But they give these very different results. And the reason for this is that apparently a couple of small assumptions here and there, for instance, the Vink prescription assumes a beta law, which means that it does not self-consistently, it doesn't base itself on physical laws, so to say, to figure out what the wind structure looks like. It just assumes a certain shape and plugs that in. And that assumption seems to have given rise to this bi-stability jump. I also think there is a thing to consider here as well, which is sort of the, how do you say this in English? I don't know, the zeitgeist, the idea of the moment was in 1995. They saw this jump as well in terminal wind speed over escape speed, so there was a reason to expect it. I'm not saying they put it in there on purpose, but if you expect to find something, you're going to agree more with your result when it is there. That's just the way we work. We cannot work around that. While in 2023 and 2024, this idea of this jump in terminal wind speed over escape speed had been kind of subdued already. There were multiple observations, including from Paul Kruijters here, that showed that maybe this thing is not really there. So them not find, they didn't find it, partially because they used different assumptions, and because they were not expecting to find it necessarily, I think, as well. So the exact small differences between the two is hard to convey here, definitely without looking at the papers again. But the biggest difference that you can very easily see is that for the Vink rates, for the Vink prescriptions, they used models which does not self-consistently compute the velocity structure, while for these two there are. And that's why these don't have a bi-stability jump, while this one does, I think. I think that has to do with it somehow, because that is the biggest difference between the models.
And you mentioned the beta law, but doesn't Fastwind use a beta law as an assumption?
Yeah. Yes, it does use a beta law as an assumption. And I actually, at some point, I think in the thesis, hint to it, because a beta law has this very particular shape, and it depends on a parameter. Beta, luckily, otherwise the name would be horrible. The beta, and that beta, you want to be in a value between up to 2. Everything higher than 2 becomes a bit awkward, because that means that you're slowing down the wind a lot. In a particular region of temperatures, I find that I need to have betas up to 4 to get a good fit. That means that probably the beta law is not really a good description of the winds over there. That also kind of coincides with this region right here in the bi-stability jump. So that kind of gives you a hint as to maybe how it is connected as well. What we should do instead, in my opinion, is there are other solutions. You could do a self-consistent solution. Fastwind has a self-consistent mode that you can base it off. The problem is you go from a computation time of 45 minutes to hours. I don't know the exact time, but let's say 2 hours. So using that for these GA modeling just becomes too slow. But there's other ways to do it. I know that there's a team that doesn't use the beta law. They use something called the delta slow solution, and you could use that instead, which has a very slow, much slower gradient to the speed, which agrees with what we see that the model wants to push to. So that would be the logical next step if you want to look at it observationally, if the beta law is a good or bad thing.
All right, so I mean, from the data you show and others, it seems that indeed this B-stability jump is not seen in the data. So my last question, and maybe I should mention for the audience, but Alex de Coter was the second author in that Vink paper. How do you feel disproving one of the famous predictions of your supervisor?
So I seem to have a track record of it, because not only am I saying, nah, this doesn't work, and that's what Alex did, but I'm also saying no to this, and that's what Yun did. So there seems to be...
I'm the next one, right?
Yeah. Yeah, I don't know yet. I'll go to do binaries in Korea now, so maybe I'll find something, but I'll have to look. Thanks.
Okay, thank you. So I'll have only one question, which is a bit more general. I was wondering if you would do something, have a possibility to do your PhD thesis again. So what would you, but with the knowledge you have now about the process and everything, what would you do differently? Would you do something differently?
I mean, yeah, there's always things you messed up, which you now know you can do correct the first time, but that's like easy. I think the biggest thing I learned over at least the last 2 years for sure is that if you keep trying to figure out everything yourself and do everything yourself, you're going to be hella slow. It just takes forever to learn everything yourself. So I feel like in the last couple of years, I've learned to, when I don't know something and I know somebody else does, don't try to do it yourself. Just let them do it, let them help you, let them explain to you how it works. Because if you're going from scratch, you don't know where to start to look, you don't know where to start to learn, you don't know the codes, you don't know anything. So I think that is one of the biggest changes. I think I would start doing that from year one. And that probably would have sped some things along, definitely in the first year. You still need to figure out these things, but it becomes a lot easier if you have somebody that already knows these things.
Teamwork.
Teamwork, yeah, I mean...
And delegating.
Yes, and delegating. It's great.
Okay, good. So now I will ask if someone in the audience have a question. Yeah.
Hi, Olivier.
Hello.
Amazing presentation.
Thank you.
I'm happy to be here. I have a question. Why don't we all together abandon all those spectroscopic models and do hydro models instance? Takes if UG is correct and most of those stars that you have are in binaries, we have estimate on the mass.
Yeah.
Luminosity is more or less constrained quantity.
Sure.
You have input parameters for your hydrodynamic models. Why don't you run similar models as Florian did? Get the wind structure, which is self-consistent, and get the spectrum out of that. Then you don't have to fit 18 parameters, but you fit 4.
4, yeah, exactly. So before I start answering the actual question, I want to disagree with one of the setups for your question. Even though they're probably in binaries, actually getting the mass out is going to be a lot harder because there is the inclination and the dependence on it. And for a lot of them, we still haven't found if there is an actual binary there. So let alone that we can constrain how it's rotating and use Kepler's laws to get the mass out. But I see your point. Your point is, okay, you're complaining about all these 18 parameters, but there are the tools to create models, as Florian has shown, which use a lot less of these parameters and still get this mass out. Now, one of the big issues is if you want to iterate over many models, this is going to be very slow because I don't remember the exact time it takes to run one 3D model, but I think we're talking on the order of weeks to months. But Nico's next to you. It can nod if that's correct. Down? Couple of weeks it is. It would take a couple of weeks to run one of these models, and then we have a nice hydrodynamical model. Indeed, like you say, self-consistent wind, everything just pops out naturally. That's fun. We still haven't gotten to the spectra yet, right? Now we have a hydrodynamical model. Computing a spectra of it has some technical issues that we're currently trying to solve, actually, in team equation or Yun's team. We're trying to solve these right now, and we're in the process of doing so, but they're not ready yet, I would say, in comparison to actual observations. I have no clue on what the time scale of that part of it is, but it's also multiple days, I think, because if I look at the data size, well, I mean, they produce terabytes of data, apparently, so it takes a while to compute them. So now we're looking at, let's say, a couple of weeks, indeed, let's keep it to the lower end, a couple of weeks for one model. Now you need to kind of hope that that one model is instantly correct, otherwise you can start all over again. Right? And this limits you immediately to a bi-eye fitting approach because doing a statistical approach for fitting now becomes unfeasible. So what you could do is sort of a hybrid in between. First do 1D fitting, figure out some of the parameters, so you're already relatively close when you do the 3D or 2D or whatever you want to do out of it. But then we still need to the final technical hurdle of actually getting the spectra out of it, doing the radiative transfer through it, still needs to happen. And we are not completely there yet. So.
Anyway, I guess it would last these 2 months, which you have to finish other things. So you will not do it.
No.
So there are some more questions.
Thank you, Olivier. So I had just time to write down 2 questions, but let's see where we come. Yeah, so you mentioned in the beginning that you have this 2-component medium and your parameters, your fit parameters are part of that physical model. Yet you argue for a multi-component medium, which is a bit strange because how can you reconcile results from a 2-component medium model and then argue for a multi-component medium if those parameters are 2-component?
Okay, so I think what you mean by your question is you start from a certain paradigm where you have 2 components, and then I compare it to your, what would you call it?
Maybe I'm wrong, like Alex.
Yeah, no.
It's possible.
So you're correct that the way we are talking about the clumping is very different, right? Like, if I go back, I think I can get the slide up. Yeah, here. So this is your result. And what you show is that there is this distribution that looks, I don't know what we call it now, log Gaussian or Gaussian. And what you're saying is, how can you in any way compare this to my results? Because my results have to have a 2-component. They always do. And this is actually pretty similar, I think, to what Alex asked, in the sense that, like, I agree that what I'm saying is not the same as what it says here. Like, what I am getting out is not this. But what I'm getting out is pushing me towards something where they are closer together, where the 2 densities need to be close together, forming some sort of Gaussian in the end anyway. So yes, I do not get this out, but I think my results show that the current prescription we have is wrong. That's why we get the large error bars. That's why we get large scatter. And one of the solutions is you.
That's very kind, but I will still ask more questions.
Damn it.
So, yeah, since we're at this figure anyway, I noticed in your talk, since this figure is concerned with mass density, yes. You were talking there's more mass in the clump or in the interclump.
Yes.
And of course, there should also be still mass in the clump. But mass and mass density are not the same, of course. No. So how should I reconcile your statement of mass or a mass distribution with a statement like this figure, which is about a density distribution?
Yes. So for ease of grasping the values, I changed from a mass density to an actual mass. I just recomputed it. But in the 2-component medium, that's actually very straightforward, except in very peculiar cases, your interclump density, which gives you the density in the interclump, that's mass density, very directly translates to a specific mass percentage. So yeah, it is just pretty much the same. It's also 40%.
Okay, and to wrap up, so you mentioned in the end you had some problems with your B supergiants and your metallicity, but couldn't be a result because your atomic database is insufficient in that regime?
So I would be surprised if that was an issue of it, because as Paul mentioned at some point, the main thing we get the mass loss rate from is H alpha. And I am doubting we have the atomic database of H alpha wrong. If we have that wrong, then we need to start all over. Like that's no way around it. But assuming we have that correct, and that is one of the more understood ones, I don't think that is going to actually resolve anything. It might change some of the temperatures we get out, and if that has some impact on getting it to O star regime, B star regime, change the luminosity maybe a bit, that could actually do something. But I am doubtful that it's going to change too much on the atomic database side.
Okay, thank you.
Thanks.
Some more questions? No? Okay, then I thank you all. And now the jury will withdraw to make the decision.
Thanks. Thank you. Thanks.
Ladies and gentlemen, dear colleagues, I will now proclaim the results of the deliberation by the examination committee appointed for granting the doctoral degree in science, astronomy and astrophysics. Olivier Verhamme has presented to the faculty the PhD thesis on the topic Spectroscopy of Massive Stars at low metallicity, studying the atmospheres and outflows of B stars, in partial fulfillment of the requirement for the PhD in science, astronomy and astrophysics. And Olivier Verhamme has defended his thesis in a public session before the examination committee. The examination committee has determined that all requirements concerning the granting of the doctoral degree that are prescribed by the law and by the university regulations have been met. Therefore, on behalf of the rector of KU Leuven, I confer upon Olivier Verhamme the degree of doctoral sciences, astronomy and astrophysics. By obtaining the doctoral degree, you commit yourself as a doctor to act also in the future in accordance with the basic principles of research integrity as described in the ALLEA European Code of Conduct: reliability, honesty, respect, and accountability. I can close the session now. Congratulations. So we are not yet fully done because I will give the word now to Jan to say a little bit about it. What? Yes.
I need to sign something.
Okay, let us sign that. You have a special pen.
I have a special pen for the occasion, yes.
Okay, so you sign.
So I sign here?
Yes. And that is yours.
That's mine. Thank you very much.
There are two versions. You have English and Dutch.
Okay.